Okay, AP Chemistry trying something new today. Just so we can get through some of these notes, we'll go over them again tomorrow. Tonight's homework is just to get the lab finished, so there won't be any homework problems tonight based on this. But this will let us spend a little more time doing some practice problems tomorrow and hopefully give us more time to review for this test and ultimately the AP test. So, jumping right in, you should have your note packet and a pen or something if you miss something, you can go back and maybe watch the video. It'll be posted on the internet. Or check with your partner. So a lot of this is going to be review. We're talking about atomic structure and specifically subatomic structure, so those particles, and a little bit about how they were discovered. More of an emphasis on the structure of an atom, though, than like a social science lesson on the particles themselves. So first of all, electrons. They were discovered by J.J. Thomson. He actually discovered them using something called a cathode ray tube. Tomorrow I'll give you an example of that. Basically, this is actually what is in your, if you have an old school like glass tube TV. So he discovered there's this like beam of something that he could move around, and he figured out that whatever was in that ray was negatively charged, because when he brought a negative charge nearby, it would bend away, and so he ended up calling them electrons. He measured, using this, based on the amount that the cathode ray curved, that the charge to mass ratio of an electron was 1.76 times 10 to the 8 coulombs, which is our measure of electrical charge per gram, which was great, but is only really useful if you know one or the other. And then if you know the charge, you can figure out the mass and vice versa. So this other guy, Robert Millikan, came along and he did something called the oil drop experiment. We'll talk about that also a little more tomorrow. In college, I actually had the opportunity to recreate this experiment and actually measure the mass and charge of a single electron myself. We'll talk about that as well. But he discovered the charge of an electron. And then using J.J. Thomson's ratio and his discovered charge, he was able to also discover the mass. So the charge of a single electron is 1.60 times 10 to the negative 19 coulombs, and the mass is 9.11 times 10 to the negative 28, which is why we end up using units like AMU. But even in an AMU, an electron is approximately 0. That's all for the electron. A little while later, Goldstein came along, discovered the proton, using cathode ray tubes and something called canal rays, but their mass was almost 2,000 times, specifically 1,836 times more than an electron. Most of the time when we talk about masses of atoms, we don't really talk about the mass changing when they ionize. It's because it's such a small factor relative to the mass of the protons and neutrons. Part of the discovery of the proton as well was Rutherford's gold foil experiment. He shot heavy, positively charged alpha particles at a thin sheet of gold foil and expected them, you might remember this from regular chem, expected them to go straight through, discovered they kind of deviated off to the side. So he figured out, okay, if positive charges are being ricocheted to the side, there must be something positive in an atom, and it must be very small, because it only ricochets some of the time. And he figured out, okay, there's a nucleus, it's positively charged, and that's how the nucleus came into, not existence, it existed before that obviously, but came into the scientific community, understanding some about the atomic structure. For some perspective, if the nucleus was the size of a 2 millimeter dot, which is about the size if I took like a pencil and I put a little dot on the screen or on your paper, then the diameter of the atom, so from side to side, would be about a third of a football field. So to the 30-yard line, little tiny pencil dot in the middle, that would be the relative scale of a nucleus in an atom. Interesting thing to think about that is, well, what's then all that space between the nucleus and the edge of the atom where those valence electrons, those outer electrons are? And the answer is that it is 100% empty space. Interesting thing we'll talk about tomorrow too as well. When we talk about the subatomic particles, we need to know that the masses of each, protons and neutrons, are both about 1 AMU. It's important to note that the neutron is just actually slightly heavier. We'll talk maybe about that later on when we do some nuclear chemistry, but for our purposes now, both are about 1 AMU. And electrons, they have a mass of 1 over 1,836 AMU, which is approximately 0 when it comes to most of our calculations. We'll factor it in sometimes, but for the most part, we can ignore the mass of an electron. The charges, protons are positive. Specifically, we can actually put a number on it, +1. Neutrons are 0, and electrons are -1. And these are all in quantities of the fundamental charge, which we mentioned earlier, that the fundamental charge of a single electron is 1.6 times 10 to the negative 19. You actually can't have a charge less than that, because you can't have a fraction of an electron, and that's the smallest charge that exists. Locations in the nucleus, you probably know this, protons and neutrons. Orbiting the nucleus, electrons. Though orbiting is a word I use very loosely there. Consequently, even though the nucleus is small, it contains almost all the mass of the atom. There's very little mass in those electrons. There is no element that we know of that has even more than 200 electrons. So even all those 200 electrons is still like a tenth of the mass of even one of the protons or neutrons in the nucleus. Very, very small factor. Almost all the mass is in the nucleus. When we talk about atoms and when we talk about nuclei, we've got a couple numbers to kind of quantify these subatomic particles. The first is the atomic number, which simply refers to the number of protons. This is the arrangement of the periodic table. It's an order of atomic number, starting with hydrogen because it has one proton, then helium, and so on. The atomic number is the determining factor for what kind of atom. And by what kind of atom, we mean what kind of element. Elements are the kinds of atoms, the flavors or brands or whatever word you want to say. So that's atomic number. Mass number then, we use the letter A to represent this. Oh, I think I forgot to uncover. Atomic number we use, that's not a number 2, that's the letter Z. So Z represents the atomic number, mass number is represented by A. And if you think about it, what are the two particles that have mass? Well, the proton and the neutron. And the mass number is also known as the atomic mass. Okay. Now this is not on the periodic table. Atomic number is on, oh, that's a highlighter, sorry, is on the periodic table. The mass number is not, but you'll see the mass number if we're talking about something like carbon 12 or carbon 13 or carbon 14. Talking about different isotopes, and that means different masses. We'll talk about isotopes more in a second. The nuclide or nuclear symbols, you might remember it from chem, we probably called it nuclear symbols back in chem, consists of 3 parts. You put the symbol of the element, which is usually E or X. I'll probably use X primarily. And then you put the mass number and the atomic number. So for example, if you're talking about carbon 14, carbon would be C, the mass, the 14, would go up top, and the atomic number, which for carbon is 6, would go on the bottom, because carbon has 6 protons, and we could deduce then if the mass is 14, that must mean that there must be 8 neutrons. 14 minus 6 gives us the 8. And then assuming this is a neutral atom of carbon, we would also know that there are 6 electrons as well. Okay. Moving along, most elements consist of atoms with the same number of protons and electrons, like I mentioned, but they have varying number of neutrons. Note that all that does is change the mass. If you change the electrons, you change the charge, but don't change the mass. If you change the protons, you change the charge, you change the mass, and you change the element. But if you change the neutrons, you only change the mass. We call these same elements with different masses, meaning different numbers of neutrons. We call them isotopes. When we mentioned atomic weight, I mentioned different isotopes here, okay, or atomic mass, excuse me. Carbon 12, carbon 13, carbon 14. There's different isotopes of carbon in the world. Scientists have gone through and calculated the average mass of atoms in a particular element, so for carbon, for example, based on the relative abundance. So carbon 12 is the most common isotope of carbon. There are other isotopes that are less common. These are also referred to as the average atomic mass. So average atomic mass, atomic weight, these are the same thing. For carbon, this is also given on the periodic table. So for carbon, it might be 12.01. I forget how many sig figs our periodic table goes to. And you actually can't have, it's important to note, you can't have 12.01 protons. You can't have 12.01 protons and neutrons together. But you can have an average of 12.01 protons and neutrons in all the atoms of carbon in the universe. Again, there's some estimation on there by scientists, but 12.01, and that is in AMUs, atomic mass units. Tomorrow, together, we'll go over how to calculate atomic weight. So for right now, we will come back to this, but I want to fill out just a little bit further on. Talking about light. We'll be talking about electron structure, electron configurations. The key to understanding this is understanding what light is. Big idea here is that it carries energy, but there's 2 terms we need to know. The first is wavelength, symbolized by the Greek letter lambda. Trying to get my pen to work, L-A-M-B-D-A. It's kind of an upside down Y. And then frequency, which is nu. It kind of looks like this little, kind of a V with a tail, or like kind of a Russian, like hammer sickle. It measures the number of cycles per second. So wavelength is simply the length from one part on a wave to another. Okay, so like from this crest to this crest. The amplitude is the height of the crest. So if you change the amplitude of the wave, those crests get higher or lower. But the wavelength is like the horizontal stretching. Frequency is cycles per second, or measured in hertz, Hz, which is seconds to the -1. If you see that seconds to the -1, like in math, that's like saying 1 over seconds. So we end up with lambda, which is wavelength, nu, which is frequency. Wavelength is usually measured in meters or nanometers. Frequency is measured in hertz or per second, and c is the speed of light, which is constant for any light waves. That means visible light and light that is invisible to us. Now these 3 things are related by this equation. Now you can see that c is constant, That means that if the wavelength increases, in order to keep C constant, the frequency must decrease. So wavelength and frequency are inversely related to each other. Now, the kind of light that we usually think of is visible light, but that's only a small fraction of all the light in existence. The visible light would be, you've probably seen this in middle school, Roy G. Biv, red, orange, yellow, green, blue, violet. I also put an I in there, BIV, blue, indigo, violet, but we're okay with this. It's good to know that the lowest light energy is red. Low energy means lower frequency or smaller frequency. The light is oscillating up and down less quickly. And going back to our equation here, if it's less frequency, that means it's longer wavelength. Okay, so red has longer wavelength, lower frequency, which gives it the lowest energy. And we're not going to continue on right now to the equations. For the rest of the period, you should have some time. If you want to rewatch the video, you can try to rewatch the video to fill in some blanks. But for the rest of the period, please use this time to work on your lab write-ups, which will be due tomorrow. Good luck. Do your best. Email if you got any questions. I'll be here after school if you want to come in and take the naming quiz.